This is 4.13 regressions. We will talk about a few things. The first part is the algebra behind linear regressions. We'll briefly touch on nonlinear regressions as well at the end. Um, as part of the algebra behind linear regressions, we will talk about something called residuals, and we will talk about the coefficient of determination. The resources we will use are the cognitive reading and a PPT. Okay, the cognitive reading is just 4.13 on cognitive, and the PPT is this one right here. And this is where we will begin. So, um, linear regressions and all regressions are about mathematical ways of finding a line of best fit. Okay, regression, a mathematical way of finding a line of best fit um, between two variables on a scatter graph. So that's what we'll see. We're going to look at how to quantify relationships between two variables. Um, and as we discussed before, we want to be able to distinguish between variables that affect another variable. So which variable is the one that's independent and which is the one that's dependent. In statistics vocabulary, we call them explanatory variables and response variables. The independent being explanatory and dependent being response. So here's an example of poverty versus high school graduation rate. And this is American data. You have x-axis, high school graduation rate in percentages, and poverty in percentages on the y-axis. Looking here, we can see that there is some kind of a relationship, but which variable is affected by the other variable? Which one influences the other one? It looks like high school graduation rate, just from our contextual information and contextual knowledge of knowing poverty and high school graduation, probably the high school graduation is what helps affect whether or not you live in poverty. And so the response variable or the dependent variable could be poverty, whereas graduation rate is the explanatory variable. So that's just some contextual information of a scatter plot, some background information for a scatter plot. And the relationship, we talked about this already. This looks to me like a negative correlation, looks quite linear, and it's moderately strong. Okay. All right. So the estimate um, of poverty is something we can do using this data, this scatter plot, because it looks sort of linear with a moderately strong relationship. We can create a linear equation whereby we can substitute in the high school graduation rate and get an approximate of poverty. So you can see this negatively sloped linear equation that will, if you graph it, sort of fit on that scatter plot. We use that hat to say that it's an estimate. Okay. So let's say using that same equation from before, the high school graduation rate in Georgia is 85.1%. What poverty level does the model predict? So then we put 85.1% in for high school graduation rate, and we use the equation. Okay, just like that. And we get 12. Now, let's go back and check first. 12% is about here for poverty. Okay, so is Georgia one of these states? We don't actually know, but that's an estimate. So if we actually go and do some research, we can then compare. Um, and then here are some linear equations, some lines on the graph, and we can see that not all of these equally fit the graph and the points on the graph. Okay, so you can see that A is the best fit. So that would be out of these three options, our line of best fit. But just eyeballing is good for MYP. But for DP, AI, math, we really want to be doing this with calculations. And for SL, we just use a calculator. For HL, we also just use a calculator, but you still need to know some of the theory behind how we get the best possible line. Okay. And the idea is to use something called residuals. The best possible line is a line where you have the smallest residual, the smallest leftover data, the smallest difference between your line of best fit and the actual data points. So if you take a look at that first data point with about, I don't know, 75% graduation rate and a 15%, 15 point something percent poverty, the residual is that difference between 15% poverty and 17 whatever percent poverty in the real world, about 1%, whereas the residual for there is very, very small, basically close to zero. But the residual for this one, for example, is really high, right? 6% or something. So that's the residual. The line of best fit and the residual um the is the difference between the data and the line of best fit point. Okay, that's the residual. So it's the difference between your prediction. Your line of best fit allows you to make a prediction like we did earlier with the equation, but the accuracy of that prediction compared to the real data point is that residual. Okay, it's the observed value subtracted by the predicted value is your residual. All right. So if you use your line of best fit, you're going to predict about an 11% poverty rate, but the real poverty rate for DC is not 11%. It's more like 17 something percent, and we get a 5.44% more. So that's your residual. The residual for that state, whatever that is, Rhode Island, um, the difference is from about 14.5 to about 10.5, somewhere about 4% residual. You might notice, however, that the residuals can be negative or positive. So given that the line of best fit minimizes the residuals, if you sum up the residuals, you're not going to get a very big number. The negative ones will cancel out with the positive ones. Okay. So that's the foundation. That's residuals. We'll get to the technique for how to use them later. Um, and another review of the vocabulary, there's correlation, which is the strength of the linear association between two variables. How well does one variable linearly predict the other variable? The higher the correlation, the closer the number is to 1 or -1. The lower the correlation, the closer the number is to 0. Okay, so if you look at the correlation here, it's a downward slope. So really, we're looking at a negative correlation. Um, and we know that the correlation cannot be greater than 1. Um, and it's between 0 and 1 in absolute terms. So a pretty strong correlation is what we see in the graph. I would say it's probably 0.75 negative. Okay. All right. Here's another graph. We can see the correlation of about half here, like that line. Okay. Another one here. This one is a little bit of a trick question. Correlation is linear by definition. So A looks perfectly quadratic, but it wouldn't be a strong linear correlation, whereas B would be. Okay. It would be a linear relationship between two variables. All right. So now let's use what we've just reviewed and what we've just learned with the residuals to see how regression works. The idea of finding the best fit line is aligned with small residuals. As long as the absolute value of the residuals, the sum of the absolute value of all the residuals, so if we go back to that picture, we want differences between the line and numbers, like between DC and Rhode Island, to be the smallest as possible, the total difference. Okay, so that's the idea. We want to minimize the residuals, the sum of the residuals. And we also minimize, another way to do this is to minimize the sum of the squared residuals. Notice that both methods will give you positive values. We mentioned earlier that the residuals will cancel each other out if you add them the way without any manipulation. That's why we have the few different options for manipulating the residuals. We take the magnitude or we do the least squares. Okay, so least squares is the most commonly used technique because it's easier to do by hand and using software. And and it also emphasizes um, extremes. We don't want um, big residuals. So the squares of the residuals will emphasize and give a lot of weight to those, and then we can then try to minimize those. So the idea is that we want a model, the regression, to be, well, we would prefer a model that is super accurate for a few values, well, a model that's super accurate for a few values, but inaccurate for most is okay as long as those inaccuracies are not big. We would not want a model that's super accurate for a few values and super inaccurate for a lot of values also. Okay, so the other way to think about that is a residual twice as large is usually really, really bad. Um, we don't want models that make hugely inaccurate predictions. We would prefer a model that always makes slightly inaccurate predictions than a model that sometimes makes accurate predictions, sometimes makes super inaccurate predictions. And the least squared method kind of deals with that. Okay. Right. So the least squares line is just a linear equation where the y value is your predictive value. Um, your intercept is the gamma zero, and you have a slope, okay, with your explanatory variable. It's just a linear equation. Um, so it has to be linear. We have nearly normal residuals and constant variability. So basically, we want small residuals, and we want the differences between each data point to be quite constant. So if your line is always a little bit off, but by a small amount each time, it gives a predictable model. It's a model that you can use with, and you know the weaknesses of the model. You know that the prediction will be off by between this much and that much. And you don't want a model that's unpredictable, where one value could be super accurate, one value is way, way inaccurate, and you don't know which one is which. Okay, right? So here's an example um, of using some of the data. If you see, this is that Rhode Island and Washington, D.C. data from before, and we have our line of best fit over here. And we see a residual of 4.16 for Rhode Island, if you remember that. Another way to think about this is if you plot your line of best fit as a horizontal line, you don't want those extremes, right? You want the lines to be as close to your best fit as possible. That's another way to visualize it. Um, right. So we don't want any unusual observations that break the trend. Okay. So the way to do that is to check a histogram. Um, and that could be helpful. We also want most of the data points to be the differences between the line to be roughly the same. Okay, so we talked about this before. All right, this idea is called homeoscedasticity. The more varied the points, the worse it is. All right. So just to remind you that these conditions, this theory is not relevant in application as much. Um, but it's good to know anyway. All right. So that's just the part of the thinking behind regressions, linear regressions. All right. So if you look at this example, this model um, has not constant variability, right? And it's not a linear relationship. So the normal residuals are the residuals are also not normal, yeah. But it's definitely not a linear relationship. You see, it looks quadratic, right? And then this one, you see the variability is quite small down there and quite big down there, right? Okay. Um, so these are some of the times when your correlational model could have weaknesses. So that's good to know. You might have an exam question where there's a linear model fitted over quadratic data, or you might have a model with inconstant variability or variable variability. All right. Okay. So we don't have to know the um, hand calculations, but really um, the way you would calculate the slope of a regression line and the way the calculator does it is you do the you take the ratios between the sum of the y residuals and the sum of the x residuals. Okay, and that gives you a slope, right? So, and then the y-intercept, then the regression line always passes through the mean point. So you use that. So you use the slope, you use the mean point, which would be if you average all the x values, average all the y values to get a mean point. And then you use that to find the intercept. So then that's how you get um, a least squares regression line. Okay. All right. So that's the algebra behind uh, regressions. There's some parts, some contextual information, and some examples of use that we can discuss now. For example, extrapolation. Um, we have this news article talking about how women will outsprint men by 2156. That is someone using a regression correlating the speed of women with the speed of men, coming up with a graph and then saying, oh, you know what? One graph is going this way, one graph is going the right way, and we're going to see that eventually we will pass, right? So then the visual look is this one right here, where you can see, oh, the speed, the winning time, the fastest time is going down faster for women. So maybe one day women will surpass men. So that's one example of using extrapolation. You might notice that extrapolation is not ideal. It uses math and it stretches it, right? To beyond where you have your data points. And that's always a risky thing to do. Okay. And the strength of a linear model is evaluated using R squared. In our syllabus, it's called the coefficient of determination. What it means is how well does one variable predict the other variable. It's the same as the R value in effect. So then you might see, for example, that the data for men has a very, very strong R value, and so does the data for women, although less strong R value. So less strong coefficient of determination. All right. It's the square of the correlation coefficient. Oh, well, it's the square of the R value, R squared. Okay. But they both say the same thing. How well does the explanatory variable predict the response variable? So if we go back all the way back to that data with poverty and high school graduation rate, you might see that, yeah, the R value will be lower for these numbers. In general, the data are more spread out compared to the sprint times that we saw here. Okay, all right. So that's the R value. So let's say this one. All right, we have an example of how to use the R squared value or the R value. Um, we'll use both in our syllabus and in our exams. They both say similar things, right? The R squared value, strength of the correlation. let's say we have this graph here. What's the correct interpretation of an R value that's negative 0.75 and R squared value of 0.560? So this helps us tease out the differences between these two, right? So that negative one tells you it's a negative correlation, but it tells you the R squared value here tells you the correlation is moderately strong, right? So that's something along those lines, all right? So 56% of the variability is explained by the model, in other words. Okay. So that's what that 0.56% means. The model is that accurate, basically. It's a percentage. Okay. So you can get some outliers in linear regressions as well. You get outliers where there's a bunch of data that fits really well, and then there's a bunch of data that does not, right? Where if you use your calculation, if you just look on the left side of the graph, you get a beautiful line. But then if you add these outliers, the line will suddenly have a less steep slope, and then that will influence the model, right? Or if you have a really, really weird outlier like that, a really, really big number that will pull your graph up, and make what looks like a linear relationship, where really it's just a jumbly mess of points. Okay, there's actually no relationship, right? Not really between X and Y, except that outlier forces there to look like there's a relationship. Okay, so here's another definition of outliers. It's really the more realistic definition that we use in everyday life. The mathematical definition of 1.5 times IQR above Q3, 1.5 times IQR below Q3. That definition is really just to teach students the idea of the outlier. But the main idea is if there are FVC data points that don't fit. Um, okay. Um, and the other vocabulary we don't actually need to know. Let's yeah, that's it for some of the math behind regression. Let's do some recapping. Um, the mathematical way, the mathematical way uh, to do a regression is to minimize residuals or the difference between observed values and predicted values. Okay, it's the exact method. We never have to do it. The calculator always does it, but just know that no matter what regression you use, whether it's linear or non-linear, we then minimize the difference between the observed values and the predicted values. Um, Finally, we have a way to measure the strength of a regression using the coefficient of determination. R squared. Okay. Whereas the R value also tells you the strength of the correlation. It also tells you the direction, negative or positive. The R squared tells you the strength, just the strength. So it tells you how much of the response variable is explained by the explanatory variable. Okay, so that's the algebra behind linear regressions. I'll pause this here and I'll do a new recording very, very quickly on nonlinear regressions. So I'll stop my share.